That's always the goal. Okay, rate of change of polar function. Okay, let's back up a little bit and remind ourselves rate of change back in Cartesian land in x's and y's before we worry about rate of change in polars, right? Like one step at a time here. Average rate of change of a polar function, again, hold off on that. Let's go average rate of change in the Cartesian coordinate system. Average rate of change, do you remember how to find the average rate of change, or what average rate of change is a fancy word for? Slope. It's just slope. Average rate of change is like good old algebra slope. Change in y over change in x. So this would be f of 5 minus f of negative 2 all over 5 minus negative 2. Right, that's old information. We haven't done it in a while, but that's old stuff. Average rate of change is the same thing as algebra slope. That's a good thing to remember. I remember that was like the bonus on like 4 of the first semester tests, right? Find the average rate of change of whatever, and people finally remembered what it was. We kept doing that because this is an important calculus thing. So that's why we're hitting it again here. Okay, f of 5 just means plug 5 in, let's see what we get. Let's see, 5 minus 3 squared would be 4 minus 2 is 2. F of negative 2, so negative 2 minus 3 squared minus 2. That would be 25 minus 2 is 23. So 2 minus 23 over 7, negative 21 over 7 equals negative 3. Average rate of change is the slope. The slope is the average rate of change. The average rate of change is the slope. The slope is the average rate of change. If you lock those two words together, you'll be well prepared for calculus next year. What's that?
What did you say?
I said if you know that average rate of change means slope and slope means average rate of change, you'll be well prepared for calculus next year.
Oh, okay.
You guys are just desperate to see a quiz for some reason. Number 2, the average rate of change for a polar function, here's good news, is the same thing. So again, it's hard to visualize like slope on a polar graph because it's not like a rise over run, because you don't really have rises and runs and polars. But it's still change in this case, g over change in theta. So it's still the dependent variable over the independent variable, if you want to use the fancy words. So the average rate of change from pi over 3 to 4 pi over 3 means, well, let's plug in 4 pi over 3 and plug in pi over 3. That would be the y values. Shouldn't say y values because they're not y values. Those are the g values. And then the thetas would be 4 pi over 3 minus pi over 3. So it's like the process is exactly the same. Change in y over change in x. Change in g over change in theta. So I've got to do a little bit of work here. Oh, look, still got to know the unit circle. When will it ever go away? Never is the short answer to that question. Cosine 4 pi over 3. It'll never go away. And will I ever have to stop drawing it? I don't know. So cosine 4 pi over 3 would be negative 1/2. So negative 3 minus 5 is negative 8. G of pi over 3. 6 cosine pi over 3 minus 5. Cosine pi over 3, that was easier. That's a half. 6 times a half is 3. 3 minus 5 is negative 2. So plug those back into the slope. Again, it is the slope formula, but it doesn't really mean like rise over run on the picture, so be careful using the word. We know what you would mean. y2 minus y1 over x2 minus x1. So let's see, that would be negative 6 over pi. That's kind of a weird answer, but there's nothing I could do to simplify that. So that's my average rate of change of that function between pi over 3 and 4 pi over 3. In the above problem, if r has units of centimeters, what would the units of the average rate of change be with respect to theta? Well, so change in g would be in centimeters. Theta is in radians because it's always in radians. So centimeters per radian. Right, you do that in physics a lot, right? Even if you don't know the unit before you get the answer, like the formula also tells you the units. Not that you would forget the units of like velocity, but distance over time, so that's miles per hour. And you're like, oh yeah, velocity has units of miles per hour. Now that's an easy one, but that's what you do in physics and even chemistry when you get to some of those crazier things. Or you do it the other way, like you know the unit, you don't know the formula, so you use the units to figure out the formula. So like that's how I survived chemistry and physics in college. I figure it out without really understanding what's going on. Not the best way to go, but gets the job done. Number 3, we can use the average rate of change to approximate a function value. So sort of using the idea of a slope, like we don't know what's going on in between the two dots, but my average rate of change line means I could use that to approximate what's going on in between my 2 points. I don't know what's going on in between them. That may not be exact, but it'll be close enough. Okay, f is a continuous function with values in the table. So we're back to x and y here. That makes things a little bit nicer. Use the average rate of change on negative 3 to negative 2 to approximate the value of negative 2.5. So average rate of change. We're back to just good old algebra 1 slope here. Between negative 3 and negative 2. You probably remember it doesn't really matter what order you do, like big one minus little one or little one minus big one, as long as you do the same in the top and the bottom. Yes, you're right, it is a positive 2. Okay, f of 2, I can just look at the picture. Wait a minute. I think it's supposed to be negative because I don't have a... So I was right and didn't know it a minute ago. I think it should be negative because I don't have a positive 2 on my table. So let's make that negative again. So I was wrong but right, and you were right but wrong. So let's fix it. F of negative 2 would be negative 1. F of negative 3 is 5. Over, keep track of who's negative down here. Negative 2 plus 3 would be 1. So all that to say, negative 6. Thank you. Which, maybe if I had just paused and looked at that, our change in x was 1, our change in y was negative 6. Maybe I should have just done it that way. So my slope is negative 6. Again, that's the same thing as the average rate of change. That's the slope. That's not my answer, though. My answer is if I use that slope to get from negative 3 toward negative 2.5, so f of negative 2.5, let's see. So I'm going to start at f of negative 3. And I'm going to go up by, let's see, put this in words, slope times change in x. Because slope is change in y over change in x. So if I figure out what my x step is, I'll multiply that by y, and that will give me my change in y, which is what I want. So my y value starts at 5. My slope is negative 6, but I'm not going to take a full step. I'm going to take from negative 2 to negative 2.5 to 3 means my step, what's my step size going to be? It's just a half. From negative 3 to negative 2.5, that's a step of a half. So 5.
Would it be negative? Is it 5?
Oops. If I'm going from negative 3 to negative 2.5, that'd be a slope of a half. Yeah. Or a step of a half. So 5 minus 3 is 2. Yeah, normally I'm stepping down by 6, but that's if I went a full step over. If I go half a step over, I'm going to step down by 3. So I'm going to guess that f of negative 2.5 is approximately equal to 2. Because I don't know that it's a line that connects the two. I'm using this approximation here. I'm using the slope to approximate that. We do this a lot in calculus. I'm thinking that because we did it twice today in first period. Use the slope to approximate the next value. Okay, well let's do the same thing, but now in polar world. Let r equals h of theta be the polar function defined by 2 plus cosine. Approximate the value of h of 5 pi over 12 using the average rate of change between pi over 3 and pi over 2. Ooh, this is going to have lots of fractions in it. I have to be super careful here. So, average rate of change, that's the easy part. That's good old Algebra 1 slope. Again, it's not exactly the same thing here in terms of the graph. It is sort of the same thing in terms of the formula. H of pi over 2 minus h of pi over 3 over pi over 2 minus pi over 3. Yeah. Fractions, unit circle, all those old things that we're so good at. So let's see, h of pi over 2 is 2 plus cosine pi over 2. Let's see if they gave us nice numbers to work with or not. Well, that's definitely a nice number, because cosine pi over 2 is 0, right? So that's just 2. H of pi over 3, 2 plus cosine pi over 3. That's not awful, but it's not as nice as 2. 2.5. So you go 2.5 or you can go 5 halves. Either way. At least there weren't any square roots in there, so it's not as bad as it could have been. So 2 minus 5 halves over pi over 2 minus pi over 3. Oh man, we got algebra here. What do you want to do to solve that? Like, I'm just curious now. Like, you got algebra options here. What is your choice to what to do next? A few of you are like, no, I'm not going to do it.
You do a conjugate thing?
I don't think I do a conjugate thing, like multiply by the plus.
Common denominator.
So the two options are common denominator of the top and the bottom, and then keep it, change it, flip it. That's one way to go.
Like simplify the top and bottom, and then you can flip like 2 minus 5 halves, and then pi over 2 minus pi over 3.
Yeah, that's what Addison's saying. Yes. So simplify the top, simplify the bottom, and then keep it, change it, flip it. There is one other thing you could do, but if nobody sees that other thing, then let's just keep it simple here. So 2 minus 5 halves would be negative 1 half. What the other thing you could do is multiply the top and bottom by 6. That would cancel everybody. You still might. No, you wouldn't have to keep it, change it, flip it, because you'd get rid of the fractions. But nobody wanted to do that. You all wanted to do probably the more straightforward thing. Pi over 2 minus pi over 3. So that'd be 3/6 minus 2/6. Would be pi over 6. And then keep it, change it, flip it. So negative 1 half times 6 over pi would be negative 3 over pi. Now, that's not my answer. That's the average rate of change. So as I move from pi over 3 to pi over 2, I'm changing. I'm going down 3 over pi for every radian that we go. So let's see. We want to land at 5 pi over 12. We will start at, which one do we start at? Well, I guess you could start at either. It's probably easier to start at the lower one, because then you're thinking about, you're adding. Your step is adding rather than stepping backwards. But you're right, you could start at either one. I'm going to start at the lower one. And then I'm going to add my average rate of change times my change in theta. Uh-oh, my change in theta. How far is it from pi over 3 to 5 pi over 12? The short answer is I don't know. That's why we do common denominators here. So yeah, that would just be pi over 12. 5/12 minus 4/12 is pi 12. So pi over 12 is the step that I'm going to take from pi over 3. I'm going to step over pi over 12 to get to 5 pi over 12. H of pi over 3, we already have that written down somewhere, 5 halves. Plus, the pi's cancel, plus negative 1/4. That was kind of nice. More fraction work. 10/4 minus 1/4 is 9/4. So h of 5 pi over 12, I shouldn't say equal, I need to put a little squiggly line on there, is approximately 9/4.
How did you get the formula where it's h of 5 pi over 12, which is equal to h pi over 3?
Because I'm going to start at pi over 3. I'm going to step over pi over 12, and that's going to land me at 5 pi over 12. So it's not like a memorized formula. It's like a, where do I start, how far do I go, and where does that end? And all those are connected to each other. And with each step, my rate of change is negative 3 pi over 12. So that's why I multiply those. That's how steep the line is, although it's not really steep because we're on a polar curve rather than a rectangular curve.
Where did you get 5 pi over 3?
Because my y value at pi over 3 was 5 over 2. That's the y value I'm starting at. don't know if it's worth it to like sketch out a full picture here, but we're going from pi over 3 to pi over 2. Our pi over 3 value is 5/2. Our pi over 2 value is 2. 5 pi over 12 was in the middle, not directly in the middle, because that would have been too easy. Like right there. And so what we were doing is, well, let's just play connect the dots and figure out where that point is. And so my step was pi over 12. That's where that came from. My average rate of change, my slope was negative 3 over pi. So I multiplied those together, and that gets me, this is like this combination of things is this height. So that height is negative 1/4. So I stepped down by 1/4 from where I started. That's sort of the visual. But again, I'm representing this in the XY plane because drawing it in the polar plane would be even worse. So yeah, you do the same thing from XY to polar, but it's just hard to visualize. Number 5. The table gives values of a polar function for selected values of theta. If the value of f of pi over 12 is estimated using the average rate of change. Okay, so this is like the actual value is 1/2, but if we use the average rate of change to estimate it, which of the following is true? So I need to figure out what I sort of need to ignore this point for now, right? I don't want to mark it out because I need it. So I'm going to estimate this and then compare and see which, is it over or under and by how much. So average rate of change, that's just the slope. This one's kind of nice because all the values are right there. So 7/8 minus 1/4, change in y, over change in x, pi over 6 minus 0. We get a lovely fraction works again. 7/8 minus 2/8 is 5/8 over pi over 6. So keep it, change it, flip it. Let's see, we get a little bit of reducing, not much. 3 and 4, so 15 over 4 pi is my average rate of change. So f of pi over 12 is start at f of 0, average rate of change times the step size. Step size is easy when you're starting at 0. So my step is only pi over 12. So f of 0 is 1/4. Pi's cancel. And fractions are just brutal here. 15 over... Oh, that does a little bit of reducing. I could reduce by... Because I'm stepping from 0 to pi over 12. Again, even though it's not a rectangular graph, it might be easier anyway to like lay out the XY thing and plot and kind of graph it out if you're more visual. Let's see, divide by 3, yes, 5/16. 4/16. It's my. Yeah, I should have reduced the 15 and the 12 to start with, and I would have landed at 5/16. So either way, But yes, that would have been a smarter way to go. 4/16 plus 5/16 is 9/16. Whoops, this was an approximation though. That was the whole point of this problem. My approximation is 9/16. My actual from the table is 1/2. So my approximation is over. So over by a 16th. Yeah, 9/16 to 1/2. Goodness, fraction is brutal. So I'm over by a 16th. The approximation would be an overestimate by a 16th. Oof, algebra. Fractions and pies. Okay, relative extrema. And again, we'll start with an XY graph because that's pretty easy to do, relative extrema for an XY graph. Recall the concept of relative extrema from an XY plane. So how many relative maximums does this graph have? How many relative maximums? Back to an easy question here. What's that? 3. People are like, oh, 3? I'm so confused. Fractions have fried my brain. 1, 2, 3. 3 peaks, so 3 relative maximums. How about relative minimums? So valleys, 1, 2, 3. Also 3. Points of inflection. We've had problems counting points of inflection before. Remember, that's where it changes from smiling to frowning. So I'd say there's one somewhere in there, right? I don't know exactly where it is, but somewhere in there it changes from smiling to frowning. And then somewhere in there, there, and well, not anymore. It's frowning from there on. So 5. Excuse me. Okay, max and mins on a XY plane, no big deal. Maximum and minimums on a polar curve, more confusing. And we pulled that from College Board, and then the more Miss Murray and I looked at it, we're like, that's not even right. So I'm going to hold off on why it's not right, and let's just say, meh, that's not good. Instead, let's look at this picture. Use this definition. No, we don't want to use that definition. We want to use the idea of maximum now is not, or extremum now, is not highest and lowest. It's more like farthest from the origin. Because R isn't measuring how high or low we go, R is measuring how far out we go. So let's mark the points on this graph that have a relative, and again I'm going to mark out the word maximum and just say a relative extremum. Maybe I'll explain why in a moment. So how many farthest out points are there? 4. Mark the points on the graph. Oh, I didn't ask how many. He just said mark the points on the graph. So those farthest out points, those extreme points, are those 4 outermost parts of the petals. Pardon? It's like, that's not hard. The trick is some of those are maximums and some of those are minimums. That's the weird part. But we're not going to worry about that. We're going to just say, you know what, let's just call them extremums, and then we don't have to worry about whether they're maximums or minimums. The minimums happen when you reach a -4. Yeah, we'll just leave it like that for now. So the maximum and minimum versus just saying extremum is the tricky part. Here's my attempt at humor. Polar maximum minimum, no thank you. But if we just say extrema, then we don't have to worry about, well, are these points at +4 or -4? There's no way to know just looking at the picture. Instead, we'll just say, well, they're 4 away, so it's an extrema. Does that make sense? Like, because unless you know the equation, you don't know if this point is a -4, pi/2, or if it's +4, 3 pi/2. And the good news is we're not going to have to worry about it, because we're going to give this motion to the maximum and minimum, and instead just go with extrema. The trick is, College Board tries to split the difference and it doesn't work. So throw that out. Okay, number 8. A polar function is given by this thing. Determine all the values of theta at which the graph has a relative, whoops, we don't want to go maximum, we'll just say extremum. Because if it says maximum, then we got to differentiate between the positives and the negatives, and we don't want to mess with that. I think what would be easiest is if we just did a graph of this. That would at least tell us how many, right? We could just count, and we would at least know how many we were working with. What's this shape? 8 petal rows. 8 petal rows. It's a sign. What does that mean for roses? Yeah, it means not on the x-axis. It's also not on the y-axis, but the main thing is not on the x-axis. So 8 petals, equally spaced, that'd be 2 per quadrant. So I can kind of just sketch these in here. Again, they're supposed to be equally spaced and equally sized. These are roughly equally spaced. They're not so much equally sized. But we get the idea. So how many? Oh, you know what? I should have been careful about. 0 to 2 pi. So I'm going all the way around. If it was 0 to pi, I'd have to really back up and think about what's happening. That would be. I assume there'd be half as many. So 8 petal rows. So I guess we already knew there should be 8 answers. There's 8 extrema. And we know where they are. Well, we don't know their theta location. We do know their location on the picture, like all of those places. And so those values, so 8 extrema at r equals, right, how far out does this thing go? 6. Oh, here's where my circle is. Draw a circle, it makes them look better than normal. So at 6 or -6, we don't really know which ones are 6 and -6. We can't tell by looking. But that's okay. We'll cover this when we get to the formula. So 6 sine 4 theta equals 6. Or 6 sine 4 theta equals -6. Okay, so this is like old school last test, solving equations. Sine 4 theta is 1. So where is sine equal to 1? What angle has a sine of 1? Pi/2. Only pi/2. Yeah. Now, because of the 4, though, I need to I need to start going around more than once here. So pi/2 plus 2 pi, that would be 5 pi/2, and 9 pi/2, and 13 pi/2, And how do I know to stop at 13 pi over 2?
Because it's 2.
There's two ways to answer that question. One is, if the answer is 4, I know I should have 4 answers, or well, 4 here and 4 there. That's one way to do it. The other way is 4 pi needs to be between 0 and, or excuse me, 4 theta needs to be between 0 and 8 pi, and the next one would be past 8 pi. But probably the easier way is, look at my picture. I should have 4 answers from this side and 4 answers from this side. So theta is -1. That's on the down spot. So that's 3 pi over 2. And then it's plus 2 pi. It's also sort of, it fits every other one of those. 15 pi over 2. And then that's not really my answer because those are the 4 thetas. So if I divide everybody by 4, all my denominators are 8. And I'm going to leave them in this order. I guess that's out of order. So if you wanted to put them in order, that would be fine. I'm leaving them out of order because there is still a process there. They're grouped by where it's a max and where it's a min. Those are maxes. Those are mins, but because of the confusion, we're not worried about that. We're just going to say they're all extremas. And this sort of makes sense because this one would be pi over 8. And this one would be 3 pi over 8. And 5 pi over 8. And you could count all the way around and probably land at 15 over 8. 1, 3, 5, 7, 9, 11, 13, 15. So I feel like I got them all. And again, College Board is kind of weird on whether they think those are all maxes or like in part of their definition they would say all of these are maxes, but in another part of the definition it would differentiate between the maxes and the mins. That's why we're going with extrema and not worried about it. All right, one more. Which of the following is false? Read carefully here. If R is positive and increasing, then a distance from a point on F and the origin is increasing. So if R is positive and increasing, then yes, we're getting further away. Like I'm just thinking about R getting bigger. Positive and getting bigger. That's true. And I bet I could work this problem by, if it changes one of these things, it probably changes this answer. So positive and decreasing is probably decreasing. If R is positive and decreasing, so it's getting smaller, so it's getting closer to the origin, then yeah, that distance is decreasing, so that's true. Again, we changed one thing, so we should probably change that. That's another way to think of this. Positive increase or negative increasing. Well, if we change one of these, this is probably supposed to be decreasing. If R is negative and increasing. Negative and increasing. So it's like going from -4 to -3 to -2 to -1. Well, that distance then is actually decreasing. We're getting closer to the origin. So that one's not right. And then that last one, negative and decreasing. So -2, -3, -4, -5. We're getting further away from the origin, so that's true. Again, it's the negative stuff that really messes things up on the polar graphs. Okay, so two main things today. average rate of change, which is sort of the same as Cartesian. Like the formula is the same, the process is the same. If you try to think about what it looks like on the graph, it's really wacky. The slope of a polar curve, that's a calculus question that you'll worry about next year if you take BC. And then relative extrema, we're not worried about maximums and minimums. That's the key point.